Temperature is a measure of the average kinetic energy within a sample. So you can take any kind of container, you stick a thermometer in it, and what the thermometer is going to do is read the average energy within it. Okay? Energy typically does not get units of Fahrenheit, Celsius, or Kelvin. Energy typically has other units associated with it. The Fahrenheit, Celsius, and Kelvin are really human ways to quantify that energy without getting too energy-y would be kind of a way to describe it. So it's more as a way to just kind of roughly ballpark some level in it. And when we have that scale, we now have a way of looking at a system and saying, well, it's 70 degrees Fahrenheit outside. We go, well, that's a relatively low energy or a comfortable energy. We associate our kind of feeling with that general temperature. Okay? If we jumped it up to say, well, it's 100 degrees Celsius outside, now we know we'd probably be boiling. Okay? And so we associate different kind of phenomenon with those numerical values or those measurements. Okay? Why might we have different temperature scales or different ways to monitor that temperature? So context for sure works for Kelvin, but between Celsius and Fahrenheit, that one's a little bit weirder. When did we use temperature to deal with? Okay, when we said 100 degrees Celsius, what do you think? What's that? Okay, when we say 100 degrees Fahrenheit, what do you think? It's a hot day. When we said 70 degrees Fahrenheit. A normal day, or it's a nice day. Okay, so you're associating those numerical values with your experience. So temperatures are an experience-based kind of rating of our environment. That's a really hot day, that's a really cold day. So they're largely based off of the human experience. Why might we have different scales for temperature then? How many times around the world would an individual human have an experience? A lot. Okay, so the observable phenomenon of this temperature change or the energy change and how we respond to it is now widely accepted. Okay? Everybody's going to come up with some way that we can quantify it. Okay, well, it's hot. Okay? When we say hot in Arizona, we're probably referencing 105 plus, maybe 110. Europe went through a heat wave where their max heats were 90 degrees, 95. Like, what are you complaining about? They don't have AC, so give them a little bit of a break. Okay? So hot is too relative of a term, okay, or too ambiguous. So we come up with a graduated system that allows us to now accurately represent that energy. So we can now compare different temperatures around the world or different experiences. What we then go through and find is that we could use that to do experiences with different observables, like ice being really, really cold or solid, okay? Or gaseous water being really, really, really hot. So we can start to now layer our human experience on top of a chemical experience to now expand kind of that definition outwards. That gets us some pretty big ranges that we could generate, and that's ultimately how we get Fahrenheit and Celsius, is that they came up with different observables. Okay? So for Fahrenheit, the common numbers, and I don't remember where I read this, but our common numbers for ice or water is it freezes at 32 degrees Fahrenheit. Well, why'd they pick 32? Why not pick 0? Because when you look at Celsius, it freezes at 0. Isn't 0 a nice round number? That's nice and easy. Why not pick that as my standard? Why did Fahrenheit pick 32? It's kind of a random number, isn't it? Are things colder than ice? Yeah. In Fahrenheit's experience, the coldest thing they had was 0 degrees, or 0 degrees Fahrenheit, which is 32 degrees below the freezing point of ice or water. So where he was physically located, his human experience did not express something lower than 0 degrees Fahrenheit. So he established the lowest temperature to be 0 Fahrenheit. He then based where water was relative to that coldest he'd ever been able to feel. Okay? So Fahrenheit then established 32 as the freezing point for water. And then you get the boiling point further up the line. Okay, when we move to Celsius, they pick 0 degrees, and I don't remember the reason behind 0 degrees. It may be tied back to water. They pick, well, water's the standard. Why would you pick water as a standard? It's an insanely common substance. It's found virtually everywhere. So pick as a standard something that everybody has access to because everybody has access to it. I can now do an easy comparison outwards from it. Okay? When we move to Kelvin, Kelvin gets kind of invented because we start to notice different trends and patterns, and it typically comes from the gases where Kelvin was invented. Okay? Or not invented, but kind of created as a unit system. Okay? And within that, what we notice is that this is a measure of energy. Okay? And I can have lots of energy, and I can have very low energy. And it turns out that there's a theoretical limit to the lowest energy possible. What is the lowest energy possible?
Absolute zero.
Zero energy. Well, if I'm at zero energy, what would my temperature scale then read? 0. Okay? That's my established line. One of the things that's nice within the Kelvin scale is because 0 is now my absolute lowest, all temperature readings have what value? Positive. Whereas if I look at Fahrenheit and Celsius, they have negatives. Is that a big deal? 10 to the negative 4. Okay? Powers of 10 and negatives. We aren't really good with those. The negative sign is typically something that messes with our calculative abilities. So when we move into Kelvin, we can lose the negative and not have to worry about it when we deal with mathematics. So most science deals with the Kelvin scale. Every so often we will see some, and I'm sure people will freak out if they saw me doing this as chemists. We have other sciences that use Celsius. Okay, and ultimately, I'm using air quotes because those aren't, this is where I'll get in trouble, they aren't really sciences. Those were initial observational fields where they built a theory on top of Celsius as a measurement system. Because they built the theory on Celsius, they've taken things and controlled how that system is scaled with negatives embedded in it. If instead they'd done it off of Kelvin, we wouldn't have had to worry about those negatives. But because that field is so old, we're stuck with that historical analysis without a new analysis to take its place. Okay? So there are places where Celsius pops up in science, but for the most part, we stick with Kelvin. Very few people, if anybody, uses Fahrenheit. Why Celsius is predominantly taken over instead of Fahrenheit, I don't know, but Fahrenheit is typically only the imperial system. Okay? Or the American system. Okay? And Celsius tends to be the overwhelming one. Because again, we now have different monitoring systems. Now what are you going to be expected to do? Convert between them. Okay? And so we could go through and do conversion factors where we talked about, well, how do we convert miles to kilometers? Well, there's 1.61 kilometers in 1 mile. So we have a nice, easy conversion. Turns out these systems don't have really nice, easy conversion units, okay? And that's where we end up with these kind of convoluted formulas that come out of them. Degrees Celsius times 9 divided by 5 plus 32 equals degrees Fahrenheit. Okay? And those numbers may seem weird, but they have origins back to how those scales overlap with each other, and usually around water. Okay? Fahrenheit to Celsius is just a mathematical derivation or rearrangement of the original one. Okay, so you're just doing algebra to shift those systems around. I will give you the top one, degrees Celsius to Fahrenheit. I would expect you to do the other. Okay? Because you shouldn't be just plugging and chugging. You should plug and chug and do some algebra. Okay? The last one, to Kelvin, will only go from degrees Celsius. Remember, degrees Celsius has a stronger science foundation than the Fahrenheit. So degrees Celsius to Kelvin, all you have to do is add 273. Okay? So whatever the degree Celsius is, add 273 and you get Kelvin. Okay? That's it. You just have to memorize that one. Okay, you'll notice that in the formula I gave you down here, I do 273.15. Why 0.15? It's really simple. Are there times where you're ever like, I want to feel smart? So you ask a little kid which weighs more, a pound of feathers or a pound of lead? And then when they go through and say, well, a pound of lead weighs more, you can be, ha ha, you're an idiot. It's actually the same, and you feel better about yourself? 273.15. That's how I feel better about myself. I happen to memorize the extra 0.15. Why? I don't know. I did. It's stuck. I can't get rid of it. So now whenever I do the conversion, I always write out 273.15. Just the way it is. Okay. So yes, thank you. I now feel smarter. Okay, appropriate. The other option that we could kind of throw out there as a kind of an example is, what is the numerical value for pi? .14 is all I've memorized, and already I heard people 3.14159.275. I mean, seriously, like really? Okay. So, and for those of you being like, you're an idiot for wanting to feel smarter, you memorized a bunch of random, literally random digits with pi. Okay. You did that because you now feel better about yourself. It's perfectly all right. We all do it. Okay. I just happen to do it here. All you're responsible for is the 273. Okay? Which happens to be how many sig figs? The one that you're responsible for? 3. Remember, when we're doing our conversions, that's your primary focus. Most of our sig fig calculations are going to end with 3 sig figs for this class. Okay? So that's why the 273. Okay? So, have fun. Do a conversion. Body temperature is 98.6 degrees Fahrenheit. What is body temperature in degrees Celsius and in Kelvin? So I'd meant to actually erase the red one, and I kind of screwed that up because that was supposed to be algebra. Okay. So remember, what you're given is the one in blue. So how would we go through and solve? What would you do, given that information? Okay, so fancy words. What I believe those fancy words are ultimately saying is we're not actually plugging things in yet. We're taking our equation, subtracting 32 from both sides. So we get C times 9/5 equals F minus 32. And then C equals F minus 32, 5/9. Yeah? Now that we have that equation, we can plug in. We'd get 98.6 minus 32 times 5/9, and you get 37. Is that actually what it spit out? 37. Okay, 37. Right, and 37 degrees Celsius. Is that the correct answer? Why is it wrong?
Because it asks for Kelvin as well.
No. Well, I kind of accept that. This is the degree Celsius. Is the degree Celsius correct? 3 sig figs. 37 is technically wrong because we started with 3 sig figs, 98.6, which means our answer needs to be written as 37.0 degrees Celsius. That is now the correct degree Celsius. How do you get our kelvins? We just add 273. If I could write numbers, and I would get 310. Should I be including an extra decimal point? Or sorry, should I be including the decimal point? So there's a decimal point and the 0. Which of those two things, or both, should be gone?
The 0 should be gone.
The 0 should be gone because
That makes 4 sig figs.
that would be 4 sig figs, and I'm only allowed to carry 3. And that technically isn't true. What was our mathematical operation? Addition. How do we count sig figs when we do addition? How do you count sig figs when you do addition? The least precise place. 37.0 is measured out to the tenths place. 273 measures out to the ones. Which one's less precise? The ones, which means my answer needs to get reported to the ones place. So that last 0 should be deleted because that would be reporting to the tenths place. I'm not allowed to report out there. Okay. Should I have the decimal point?
Is it necessary?
Okay. Is that 0 here significant? Am I reporting to the ones place? Yes, which means it needs to be significant when I report this. If I get rid of the decimal point, is it significant? No. Do I need the decimal point? Yes. Okay? Questions?
Technically, can you just put decimal place there?
Yep.
Is that like right?
Yep. Absolutely.
So you can just throw in decimals because it doesn't have to.
You're not throwing in a decimal. There is one implied there. If I get rid of the decimal, it's still 310.
Yeah.
Okay? But what I'm doing is now specifying the decimal point. By specifying the decimal point, that makes the 0 significant. If I don't have the decimal point, the 0 is no longer significant. And because I know the 0 needs to be reported, I have to have that decimal point. Okay? Other questions? Okay?
It seems like a pretty important foundational thing for Sig Figs, right?
So yeah, now that I've deleted it all, nice timing, Greg. When it comes to Sig Figs, that is insanely important. You do see questions like that. They show up all over the place, like in exam 2. Will they continue to show up through the semester? Probably not. Okay? The reason why not is that to ask a multiple choice question about Sig Figs, I'm now removing possible answer choices that get at content, okay, besides Sig Figs. Okay? I'm removing my ability to put in answer choices that could be asking, how did you do that conversion right? Okay? So it limits my ability to put in multiple choice questions by testing on Sig Figs, which means when you see a multiple choice question, you probably don't have to worry about Sig Figs, unless what?
Yeah, C2.
Okay, it may not even ask you to. If I look at the answer choices for that, how would I know that this question was asking about Sig Figs?
They're all different Sig Figs.
You look at the answer choices, and what's the difference between those?
4 and 3, 2, 1.
It's just the number of Sig Figs. Okay? I don't even care what the question is, because what's this? Based on the answer choices, what am I being asked? Sig Figs. Okay? I literally don't need to worry about the conversion. I can immediately jump to now just answering this question based off of Sig Figs. As a test writer, what am I testing on? Am I testing on your ability to do Sig Figs, or do I care that you can do a degrees Fahrenheit to degrees Kelvin conversion? Okay? This is now clearly only asking about Sig Figs. Is converting from Fahrenheit to Kelvin one of the things that you're supposed to know? Yeah. I've now wasted that question on a Sig Fig thing when I could have been asking about temperature. Okay? So you will see very quickly that a question is being asked about Sig Figs if it's multiple choice, because your answer choices become limited. Really the only difference between them is Sig Figs. How could you more trickily be asked about Sig Figs? If it's a free response. Because now you go through all of that work, and if you box at the end of that and say, well, your answer is now 310.0 Kelvin, you've done the mathematics right, you've done the conversion right, but you screwed up Sig Figs. So if that was a 5-point question, you may have just gotten 4 points out of 5, because you've shown that you don't understand the Sig Fig rules. Make sense? So in a free response question, sig figs become much more important, okay? Because that I can zero in on easily without getting rid of all other content knowledge behind the question. Make sense?
So it's kind of like, it sounds like you're saying that you're less likely to directly ask a sig fig question because we should be displaying that knowledge anyways. As we
In a show your work, you will see sig figs show up. You have to express content and sig figs. In a multiple choice, you will explicitly be asked sig figs, or you will explicitly be asked content. And you can see that by looking at your answer choices. If the answer choices vary by only sig figs, it is explicitly a sig fig question. Right? If those numbers are all over the place, you aren't being asked about sig figs, you're being asked about the content. Okay? So multiple choice is explicit to sig figs. The same thing goes with the final. Okay? Reconnect. Okay, which gets us to the next fun topic, the heat concept. Okay? We talked about temperature measuring the average kinetic energy. Well, heat is also an important thing about energy, but heat measures the total energy. Well, they're both measuring the energy. Why is one different than the other? Okay? Because when we look at heat, we change the unit. We're no longer looking at degrees Celsius or Kelvin, we're looking at joules or calories. Why the sudden change in units? Why would I measure something in grams versus milliliters? It's a different system. It's a different observation. Why is temperature measured differently than heat?
Because heat is all the energy and temperature is
It's a different system. They're both measurements of the system, but in different approaches. One case we just measure the average energy, the other one we measure all of it. Right? And that's a pretty significant difference. Right? If I take a drop of coffee at 100 degrees Celsius, okay, arguably pretty hot, right? Okay, and you spill a drop of coffee on yourself, okay, you might not be happy. But is it really going to be that big a deal? No. But if I take the entire cup of coffee at 100 degrees Celsius and I spill that on myself, are there going to be a few more curse words associated with that? Why? They're both at 100 degrees Celsius. One's more heat, one has more total energy. The average kinetic energy of those particles is the same, but there's more particles. Every single one of those particles transfers that energy into my skin. If I look at a drop versus a cup, there's a lot more particles in that cup. Each of them transfers that energy across. Whereas with the drop, I only get a couple particles transferring that energy. Okay? So I don't feel quite as bad when I get the drop splashed on me as opposed to the whole pot. Kind of make sense? Okay? So heat is a way to measure all of the energy within an individual sample. Okay? We use joules or calories typically there. Okay? The next part that comes out of this is that every substance responds to heat differently. Is that really true? Does that make sense? Do you agree with that? How many of you go home and if you were going to boil a pot of water, pull out the silicon hot pad, put that on the stove, and then put the pot on top of it? No, why not? If it's silicon, it probably won't melt. What's that? What's the point of the hot pad? To keep heat from making it through, right? So if I put that on the bottom of the stove and then put the pot on top, does the pot ever feel the heat? No. By that same token, when you look at your pot, is it made of silicon? No, what is it made of? Metal. What's the difference between metal and silicon? Metals conduct heat and electricity. Nonmetals do not. So every material responds to heat differently. Because they all respond to heat differently, we might want to quantify that numerical relationship. How do they respond? That quantification is known as the specific heat. Okay? And it is, no pun intended or poor word choice, right? It is the specific amount of energy necessary to cause 1 gram of that sample to go up by 1 degree Celsius. Okay? So when I look at water, if I'm in the calorie energy system, if I take 1 gram of water to heat it up by 1 degree Celsius, I need exactly 1 calorie of energy. Okay? Remember, calorie is an arbitrary unit. Where do you think calorie was based off of? How did we determine what a calorie was? What do you think we used as our measurement device? We used water. Okay? Calorie is based around water as our solvent. Okay? I defined the energy unit, okay, to be the amount of energy. I don't know, at this point, I don't know anything about it. It's just the amount of energy I have to put in, I'm going to define now as a calorie, 1 calorie, because I'm looking at water. Okay? Everything is now based off of that. It simplifies my calculation when I look at water. Why would I want a simple calculation looking at water? Why do I care about water? It's everywhere. Virtually everything I do is used in a water solvent. So if I know the specific heat of water, I can now use that to compare out to virtually everything else. Yes?
I feel like it's kind of a relevant question.
Go for it.
Well, okay, so everything is based off of, or the calories are based off of the heat required to raise the temperature of 1 gram of water, right?
Mm-hmm.
Then how do you have things like diet sodas and things like how are those like?
So those would alter the specific heat. So if we looked at the amount of energy necessary to heat up a soda, okay, we're going to get a slightly different energy than we would for pure water. Okay? How they differ is going to be dependent on what's in it or the other materials in it. Okay? Even when you look at a diet soda, though, what is the majority of that diet soda? Water. So what is the specific heat of your diet soda going to be? Probably 1. Okay, 1 calorie per gram degree Celsius. It's not going to be that different because the majority of it is water. Okay, so it still matches that. Okay? If we decided to switch to a different unit system, say joules, okay, in a different unit system of joules, it comes out to be 4.186 joules per gram degree Celsius. Why a different unit system? Different perspective. Okay? The joule unit wasn't based off of water as my primary observable. It was based off of something else, just like Fahrenheit and Celsius. We're looking at different reasons behind the theory of that unit, and that's why we have different ones. Why might we have multiple energy terms? Well, for the same reason we have different temperature units, because they were very commonly observed. Because we have these super common observations, we have discoveries of how we monitor or quantify those in different systems. Okay? Before you get too bogged down in all those numbers, okay, ultimately what that is now a fancy conversion factor. Okay? And we could go through and use it. It's a really complex one because there's 3 units that we'd have to convert as opposed to just 2. Okay? I don't care. We're not going to use it as a conversion factor. It's there just to show you kind of the origin of specific heat. The more important part gets at what we were just talking about with our pots and pans. Okay? Which of the following substances is expected to have the largest specific heat? Okay? Well, what does that mean? What does a large specific heat mean? So instead of it being 1 calorie per gram degree Celsius, it would be 100 calories per gram degree Celsius. That means I have to add 100 calories of energy into it to cause it to go up by 1 degree Celsius. Okay? So I have to add a lot of energy in to make it go up. So that means if I touched one side of it and put a match underneath, okay, or a blowtorch underneath, I have to put a lot of blowtorching into the bottom of it before what happens? Not even before it melts. Before I feel it get hot. So what does that mean the material was? It had a high specific heat, true. What did it do with that heat? Let's flip it. Let's say it was a low specific heat. Put a blowtorch on the bottom of it, and I touch the top. I feel it hot instantly. The amount of heat I had to put in to cause it to go up by 1 degree Celsius was very, very low. What kind of material was that? Probably a metal. Why a metal? Metals conduct heat. So if it's a large specific heat, what does that mean? It's not very conductive. Because I have to put lots of energy in to cause the temperature to go up. So it's not conducting that heat. So it's probably not a metal. So what can I go through and do? So for work on this, large specific heat then means non-metal. Well, how do I know the difference between metals and non-metals? Periodic table. To the left of the staircase is metals, to the right, non-metals. So this is really a question that's coming straight out of the first unit. Can you tell the difference between a metal and a non-metal, but now based off of a physical property? Okay. The next thing that makes this a little bit more challenging, okay, we already heard the answer shouted out, so we won't stress about that. What else makes this question a little bit more challenging? Do you have to know what CA is? Not necessarily. Why not? You look at the periodic table, where is CA? To the left of the staircase, it's a metal. Do I need to know what CA is? Nope, it's a metal. Do I need to know what CR is? Nope, because left of the staircase, it's a metal. Copper. Periodic table doesn't say copper. What do I have to know? I have to know that the symbol for copper is Cu. Now that I know it's Cu, where's Cu? Left of the staircase, it's a metal. Pb I don't have to know anything about because I can look at the periodic table. Carbon, what do I have to know?
That's the last answer.
That it's a C, and as C, where is it on the periodic table? To the right of the staircase, making it a non-metal. There's my answer. Everybody get that? Okay. Within this, I want to address this because this is important. Typically, what I would see as students' notes for this is carbon, and ultimately, you probably don't even see that. We'll probably just see this. The answer was E. What use is that as a study tool? You know the answer to this question is E. What if the question now becomes smallest specific heat? Do you have any notes here that explains why you picked E? No. So what use is this answer now? It's not. This is not a useful note. This doesn't give you any information. The information that was important was to recognize that largest specific heat meant non-metal, the least conductive. Once I know it's least conductive, it's now evaluating where are those as far as metals or non-metals. So we could go through and add metal, 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 right? You've got notes now that explain why the answer is there. The same thing happens with conversions, right? Almost universally, I look at notes for conversions, and you show the beautiful long line, the end conclusion that we got to. How did you get there? Right? If you don't know how you got to the answer, your notes are useless. You need to be writing down the thought process that we use to get there. Right? Which we will probably see a little bit later with another example. Okay. After that, we've got some kind of random fact stuff from chapter 3. Physical laws, conservation of mass. We can't create or destroy matter. We've actually already used this principle. When did we use this principle? Balancing chemical equations. If I had 2 aluminums on one side, what do I have on the other? 2 aluminums. Same principle, okay? Conservation of mass. How could you get a question asked about this? How much water did I make? How do you know it's 10?
So you have coefficients.
There's no coefficients in there.
Grams. It's 2 to 1.
It's grams, right? Conservation of mass. I start with 2 grams, 8 grams. How much grams do I start with? 10 grams. How many grams should I end with? 10 grams.
I thought the coefficient was
That's
just
it.
whatever's in front of the.
Whatever is in front of the substance. What is in front of hydrogen substance?
I see.
And
Okay.
there's nothing written there. Okay? So don't reference the measurement as a coefficient.
Okay.
We want to keep that separate. Technically, you could probably call that, but because we don't want to confuse those two terms, keep it out. Okay, so let's try a new one. 8 grams of wood, 2 grams of oxygen. How much gas was formed? Why the long pause? I mean, we got 10 grams for the last one pretty quickly. We know specifically that this is 10 grams, and we know this as a total is 10 grams. Okay? Do I know how much of that 10 grams is gas versus water? No. I cannot use conservation of mass to solve this for specifically the gas. Okay? It's impossible for me to solve. All I know is the total of those must be 10 grams. If I also added that the gas was 2 grams, would you be able to tell me how much water? Yeah, now you could. What if I told you the mass of gas was 9 grams? Yeah, okay, it's the missing piece. Make sense? So when you use conservation of mass, you have to be very careful to know the context behind how and why you're using it. It's not just, well, if I add up the masses, that's the mass of my answer. Okay? It isn't. We have to make sure we know what equation we're looking at. Make sense? Okay. Einstein came along and gives us that mass and energy are related to each other, or interconvertible, meaning that if I can't destroy matter, I also can't destroy energy. They're tied. Okay, so we get now the law of conservation of mass and energy. So in our conservation of energy, what are our forms of energy? Well, we get 6 of them. What forms of energy are you aware of?
Light.
Light, heat. The name of this class? Chemistry. We should do it more as a descriptor. Chemical energy. Nuclear. Solar gets a little bit weird. That's ultimately going to be light or heat depending on how you capture it. So that's still covered already.
Physical energy.
Physical energy, you're getting at the right idea. We're talking about mechanical. Motion is a form of energy.
Isn't that like kinetic energy?
Kinetic energy is a subcategory of mechanical energy. How did we get the lights in this room? Electricity. We have electrical energy. So when we're talking about our forms of energy, ultimately what chemistry is doing is talking about how we can interconvert between any of these. Sometimes we just care about the chemical. Okay? I generate chemical energy that generates a drug that cures cancer. That's all looking at chemical energy. Okay? I could look at chemical energy that when I burn it, it causes a turbine to move, mechanical, That turbine moving generates electrical energy. The electrical energy I then ship or move across large distances to get me light. For instance, this room. Okay? So everything we do in life is now shuttling back and forth between these. We talked about nuclear energy. Okay? Does nuclear energy generate light? Yes, this is why when you watch the old school videos of atomic bombs going off, what do you end up seeing pretty much right away? The whole screen goes white. Because of all the light energy being emitted, we now can't see anything. It whitewashes everything. All that light energy comes out. Once the light has passed us, then we can start to see the waves of everything else. That's when we see the mushroom cloud and all of that. Okay? So if we wanted to light this room, we do this in Arizona, we use nuclear energy. Okay, so to light this room, we just set off an atomic bomb, and we funnel all that light towards us. No. How do we do it? Nuclear reactors. What does the nuclear reactor do? It makes water boil. Really? Yes. Okay. We boil water with nuclear energy. What does that boiled water then do? Turns into a steam. What does the steam then do? Passes a turbine. There's our mechanical. The mechanical through the turbine is converted into electrical. And the electrical then gets shipped across the country or through our state, where it can then become light. Okay, computers, more electrical. Okay, but ultimately our biggest endpoint is light. You could also look at it as mechanical elevators, right? Okay. In that process, we're causing water to boil, okay, which means the nuclear energy is actually generating heat. The heat causes the mechanical causes the electrical causes the chemical. Whoops, sorry, the electrical causes light. Okay. Every one of those steps, I can't destroy energy. So when I go through and go from nuclear to heat, okay, not all of it can get transferred across to the mechanical, which means I lose some heat. Okay? Does the mechanical perfectly translate into electrical? Okay, we can see this with combustion engines doing ultimately the same thing, that mechanical energy. What happens if you touched your car after it's been running for a while? What do you feel? It's hot. Why is it hot? It's releasing that heat energy. Is the heat energy causing your car to move? No. Okay, heat is a byproduct of almost every single one of these, particularly as transitions between them. Which means the more steps we've got, nuclear to heat to mechanical to electrical to light, that's a lot of steps. In each of those steps, what happens to the amount of energy? It decreases. Okay, and it's not that I'm losing that energy per se, I can't trap it to do what I want it to do. Which means the end result is I've lost energy out into the world. I want to be able to control that energy better. So how could I get light in here without doing all of those steps?
Chemical reaction that makes light.
Okay, I could do a chemical reaction that immediately makes light. Okay, we're looking at chemiluminescence. Right? Does it generate enough light? No. So how else could I do it? And that's still one step. How else could I get light in here without making a step? We could go outside. Instead of being class inside, let's make class outside. Now we have light. Really simple. Why do we not do that? Because it's hot, so we move inside. But now how do we get that energy that we had free access to inside? Now we need our electrical. Well, how do we get all that shifted? So it's all of that infrastructure in each of those transitions on how we try and account for those kind of accommodations. Okay. Kind of makes sense? Okay. Let's take a look. Sorry, was that a question? No? Mechanical energy. There's an entire class built around mechanical energy. It's known as physics. Okay? If you take a physics class, what are you talking about? You almost always talk about cannonballs launching. Why does physics work for cannonballs? How did the cannonball launch? An explosion. An explosion caused by Heat. So all I got to do is heat up a cannon and it explodes. I have to heat up a gunpowder so the gunpowder explodes, which builds up enough force to launch the cannonball. The gunpowder is a combustion reaction. Physics works because of, which is chemistry. Okay? Chemistry drives our physics class. For those of you that might be like, why did the chemicals combust? You're right, physics does that too. Okay? But not at that scale. Okay? So physics does win, but whatever. Our cannonball now goes from zero potential energy, or or gunpowder has a bunch of potential energy, which is now released, transferring the energy into our cannonball, making the cannonball have kinetic energy, and now it can move. Eventually, what happens to the cannonball? Okay, it flies through the air, and then it starts to drop. Why does it drop? Gravity starts to pull down on it and counteract some of that kinetic energy. Eventually, what happens? It hits the ground. What happened to all that kinetic energy? It's not just gone. It's transferred into the ground. The ground being larger can absorb that kinetic energy, and we don't really have to see much of an impact. Okay? Unless you happen to be on the ground next to it, and then you probably felt the impact. Okay? What happens with a combustion engine? We pump gas into a cylinder. Okay? Then what do we do to the gas? Okay? And this is where we get our gearheads. Yes, we compress it. Then what do you do to the compressed gas?
You're going to spark it.
You spark it. What is the spark doing?
It pushes the thingy back down.
If the spark was pushing the thingy back down, why are we compressing gas? What is the spark doing? It's igniting the gasoline that's in there as a gas. That combustion reaction produces CO2 and water. That takes up more volume than the initial gas particles, so what happens? It pushes the piston down. Okay? The piston is effectively a cannonball with gunpowder in behind it, and what do? We light our gunpowder, and what happens to the piston? It launches like a cannonball out of the cylinder. Okay? It's tied to a rotational axis that allows it to reset, but it also forces the mechanical rotation of your axle or some other car part. You can school me on that. Okay? That's leading to motion of our car. So it's a combustion reaction. What happens when we look at biology? How many people have taken a biology class? Okay, what's the energy? ATP. What is ATP? Adenosine triphosphate. What does it look like? It looks like this giant structure. I don't know, we gotta shush that, but there's our giant structure of adenosine triphosphate. What does ATP become? What is ADP? What is the difference between ATP and ADP? And don't tell me T, D, or tri-di. Okay. All that's happened is I've removed a phosphorus, okay, and ultimately 4 oxygens. A phosphorus with 4 oxygens is known as phosphate. I lose a phosphate, so it goes from triphosphate to diphosphate. By breaking that single bond, I've released enough energy that can drive virtually all forms of life in a single chemical bond. Okay? That's pretty phenomenally cool. That is chemical energy. Chemical energy that's getting transferred from one form to another in a biological system to allow us to see, to allow us to breathe, to allow us to exist, all coming from a single bond. It's a bit overstated, but it's close enough. Okay? So what we're concerned about with chemistry is ultimately energy and how we can transfer that energy around, or how we can tweak the chemical energy to get it to do what we want it to do. And that's pretty cool. Okay? So if we take a look at these 3 systems, what can you tell me we've got up here?
Solid and gas.
How do we know it's a solid, liquid, and a gas? Because what? how close the particles are, because when we talked about solids, liquids, and gases, we referenced compressibility. So the more white space we have, the more compressible, because I can now smash those atoms closer to each other. Okay? What happens to the motion of the particles? Okay. When do we go from solid to liquid to gas? They disperse. Why are they dispersing? Because they are moving faster. The faster those particles move, the more likely they spread out. Right? Is that true? What happens at 2:15? You leave. How much are you guys all moving right now? Not much. At 2:15, what starts to happen? You move more and scatter out. Right? The same thing's happening with these. Right? What's happening to temperature? As I go from a solid to a liquid, what do I have to do? I have to heat it up. As I heat it up, what happens? Heat causes the molecules to move more, which means I transition from a solid to a liquid. What happens as I continue to heat? I transition from a liquid to a gas, which means the particles move even more. Okay, so what is the relationship between kinetic energy and temperature? What happens when you increase temperature? You increase kinetic energy. They're directly related. Okay? We won't worry about that one. We'll look at this one though. Okay, you may have heard this. It's better to fill up a gas tank when it's cool in the cool morning as opposed to the warm afternoon. Why? What's that? Okay. So in the afternoon it's warmer, which causes the individual gas particles to do what? Move more, which means they become more compressible. So when I measure out a volume of it, since they're moving more, I'm measuring out less individual gas particles. The density of the substance changes. Okay? I become less dense. Because when I run a car, I'm not concerned about the volume of it, I'm concerned about the actual particles present when we do the combustion. If it's at a lower density, I'm getting less particles, which means less chemical energy to drive my car. Okay, so I want to fill it up in the cool morning. Okay? That way it's more dense, the particles aren't moving quite as much, I get more gas molecules or more liquid molecules in there, and I get more energy from my car. Okay? What is the difference in price? I did actually calculate this once. It's about 1/3 of a penny. Okay? So if anybody ever tells you you should fill up a car in the cool morning, you can tell them that you've actually discovered that it is better while the gas is filling up your car to walk around the parking lot and find spare change. You will collect more spare change by just walking around the parking lot than you will save in the process of filling your car in the cool morning. Just so you know. Who said chemistry didn't save you money? Okay. Which gets us into the new unit 8 and 9. Okay, and this is where things become really, really fun. Okay, the really, really fun part. Okay, what was our previous unit about? You got tested on 2 things on Thursday. What were those 2 primary topics?
Chemistry and English.
Fair enough. Zero in on the chemistry side of it. What were the 2 topics you got tested on?
Conversions.
Conversions?
Knowledge.
Combustion, double replacement, single replacement,
Chemical reaction.
chemical reactions. Those were 2 independent topics. Because you needed some basics of understanding to be able to deal with chemical reactions and understand how to classify them, quantify them, balance them. You also did conversions. The whole point of the conversions was to set you up with a process that would consistently and always work. Okay? That's the process that we spent the whole time talking about. Okay? Why were we talking about that process? Guess what the next unit is? You're going to take everything you learned about chemical reactions and everything you learned about conversions, and they now become one glorious thing. If you are weak with nomenclature, you can't balance reactions. Right? If you can't balance reactions or predict products, then you can't balance reactions. If you can't balance reactions, you don't know conversion factors to convert substances. You can't do virtually anything in the next unit. You need to go back and review very carefully the process. You don't have to use this process. There are other processes that work, and what we will try and do is look at some other ways to do these processes. The problem with those other methods that I've seen so far is that they take too long. Right? And for those saying, well, it was easier for me to just divide inches by 12 to get feet. That was a process. That's not a process, that's an algorithm. You've removed all understanding of what you were doing, which means you had to know the process internally. You don't know the process right now because we're moving to units that make no sense. Okay? So you have to have a process to back this up. Which means between now and Thursday, finish your book and start trying to redo conversions. Start with those basic processes and do the process. Okay? It is not about getting the right answer, it's about getting the process. Because the process will get you the answer. Okay? So, what is our process for solving this? Okay, and we'll simplify this a little bit. That's too simple. So, what is our process?
Equals mg.
And you need another thing there, which is going to become super important in this next unit. It was a little bit less important in the last unit. Nope, still with the NMG.
Writing equals mg is actually trying to solve it. That's not declaring a process.
That is the process. The process is, what are you trying to solve?
That's what I was looking for.
Okay, what are we solving for? Just milligrams?
Milligrams of aspirin.
Milligrams of aspirin. The substance is not changing in this question, so most people will ignore the substance. When we look at the past unit, the substances never changed, which meant we didn't care what the substance was. This next unit, the substance will change. We're going to care what the substance is, so you need to include that. Do you want to write out aspirin every single time? No. So what do you want to write instead? What's that? ASP. Why ASP?
Short.
That's a shorter version of it. I could get away with just A. Okay? A becomes a little bit more confusing, but not by much. Why is A not that confusing?
What is aspirin?
A is not an element on the periodic table. Okay? If we did AS, that could be a bit confusing because we have arsenic. So ASP at least elucidates that it's something else, and we may not immediately know what it is, but hopefully with reference to the question, we'd be able to figure it out.
You don't want to mix up aspirin and arsenic.
Yeah, that's a bit of a problem. Okay? Do we know what that number is? Do we know the milligrams of aspirin? No. So that is X, an unknown value. No idea what it is. Okay? I'm trying to solve for that. What am I given to start with? 325 grams of aspirin. Okay? We're trying to make those equal to each other. Okay? As soon as I know the value of x, those can become an equality. Okay? Is there another, is that right? Another equality? I think it's because I said another. I don't know. Is there another equality that's important?
Yes.
What's that other equality?
1 gram equals 1,000.
1 gram of aspirin equals 1,000 milligrams of aspirin. Are these units the same? Are these units the same? How did I scale from here to there? What did I have to do? How do I then have to scale here? Same thing. Did I multiply by 1,000? I'm not sure if I repeated that. How did I scale on the left? How do I go from 1 to 325? I multiplied by, so how would I go the other direction? Okay, I can multiply by 325. Oh, because it's a 325 gram tablet, yeah. Okay, that works as an answer. That's a phenomenal process. That is an initial stage process. The issue with that is if I now have multiple conversions, I have to do that for every single one. Let's take a look at the process that we talked about. Where do we start? Milligrams of aspirin. Interestingly, I start with the same basic tenets. Okay, where am I going? Okay, what's the next step?
What you're given,
What I'm given. What am I given?
325 grams.
Okay, and I know everybody hates this, but I'm going to say 325 grams is not right. What are you given? Grams of aspirin. Okay, the numbers, you're too bogged down in the numbers. Trust me, I know. Okay, so you need to go through and focus on the units. Grams of aspirin. Where do I want that grams of aspirin to be located? Should I be place it in the numerator or the denominator?
The top.
Why on top?
Because that's what you want in the end.
If I look at my answer, I have the substance aspirin show up in the numerator and numerator. Milligrams is a measure of course I did the units backwards, didn't I? No, we did that right, sorry. Okay. Milligrams is a measure of mass. What is grams a measure of? Mass. So mass and substance match, both in the numerator, which means grams of aspirin should be in the numerator. Now that I have the correct placement of the unit, now I can bring in the number. What's the number? 325. Okay, and I can put it over 1 to help emphasize the fact that that is in the numerator. Okay, is grams of aspirin what I want for an answer? No, so what do I need to do? I need to do some kind of conversion factor. That conversion factor needs to have grams of aspirin in the denominator. Why in the denominator? So that the units can cancel. What should show up in the numerator? Milligrams of aspirin. Okay? And I'm still hearing people drop out numbers. I'm going to tell you right now, you're wrong. Okay? For those who go, oh, I'm not wrong. You are. I know you're wrong. Let's just leave it at that. I know you're wrong. Do not use the numbers. Use the units. Okay? What would happen if I did this conversion? Grams of aspirin cancels, right? What unit would I be left with? Milligrams of aspirin. Is that what I want?
Yes.
Yes. Because I now have the unit system set up, now I can go back and say, does that conversion factor exist? Do I have the numerical information to find that, to place in front of those units? Okay. It does exist. Where should it exist? In your brain. Why should you know that it exists in your brain? I literally told you to memorize this multiple times. Okay? What if you didn't memorize it? What should you do? Okay, we can be repetitive. Yes, you should memorize it. Okay? You still didn't do it. What should you do? You're on the exam. What should you do? Look at the front of the exam. The front of the exam where you're given a bunch of information. Maybe I decided to be nice and also gave it to you. Okay, I don't think I did. Okay, so it's not there. What should you do? Not about it. Is it a multiple choice? Can I cheat and just start guessing at multiple choice answers? No. Do you know what to do if you haven't got that memorized? Okay, what do you want to do? You still have that memorized, so I'm going to say that that's not fixing it. That's still memory. You don't have it memorized. What do you do? What do you write down? You don't have anything memorized.
If you're on the test,
Yeah.
trying to solve the problem right there, and you can't
Yeah.
remember it.
Raise your hand. Why would you raise your hand? What happens when somebody raises their hand in this class? Somebody comes over you. Like I get up and walk over you and say, hey, what's up? You'd be like, I don't know this conversion factor. This one, probably what are you going to get? You should have had this memorized. I'm sorry, I can't help you. But maybe it's one that you need to raise your hand on. Maybe I meant to give it to you and I didn't. If you never ask, you don't know. So what is the conversion factor that you were told to memorize? Milli means 10 to the negative third. Where does the power of 10 go? Where does the power of 10 go? No, it does not go on the top. It does not go on the bottom. Where does the power of 10 go? Not with the middle. Next to the milligrams is starting to get a little bit better, but still wrong. Where does the 10 to the negative third go? It goes with the core or root unit. The power of 10 will always go with the core or root unit. There is no exception if you've memorized it the way you were told to memorize it. If you've decided to memorize something else, you have to memorize more information. That's on you. The core or root unit here is grams. It's the thing that shows up the same in both places, which means 10 to the negative third goes there. What goes with milligrams? 1. I can now punch it into the calculator and I get the exact same answer as up above. If we go up above, you might say, well, didn't that one say 1,000? You're right, it does, because you memorized something different. Okay? That's okay if you want to memorize that something different. The problem with memorizing that 1 gram is 1,000 milligrams is where did your power of 10 go? It went with milligrams. Does milli mean 10 to the third? No. Milli means 10 to the minus third. You memorized 1 gram is 1,000 milligrams as an algorithm because you don't like powers of 10 and negative powers of 10. The reason you did that is you don't have a calculator. What was one of the requirements for this course? A calculator. Okay? The reason why people shift to do the 1,000 milligrams as 1 gram is they don't have a calculator. You have calculators. Okay? Calculators fix that calculation so that you don't have to memorize an extra piece of information, as in where does the power of 10 sometimes go. If you memorize it as 1,000 milligrams, the power of 10 will change locations depending on your prefix. Really? How many kilograms or how many grams are in a kilogram? 1,000 what? Grams are in a kilogram. We still get 1,000, but where does the 1,000 show up? different unit. Okay? So it is entirely up to you which system you want to use. Okay? I will freely admit there are other systems. The King Henry died drinking chocolate milk, which I think I actually got right.
Yeah,
Yeah, that was amazing. Okay, I still don't know what it means.
I
Okay.
can teach you.
But that only works when dealing with powers of 10 conversions. We'll look at that in a second. Is a mole strictly a power of 10?
Yes.
6.022 times 10 to the 23rd. Yes, there's a power of 10. Is 6.022 just a power of 10? No. You can't use King Henry died drinking chocolate milk.
Well, if it was like 10 to the third, you could.
Right? If it was just 10 to the 3rd,
Well, no,
you
if it was
could.
6.022 times 10 to the third, you could use it. It's just the decimal point placement
Yeah.
is what it is.
And that's where things go sideways on you, is you start trying to use a process that worked for simple conversions. It no longer works. It's useless as soon as we move into this section. That is why we spent so much time talking about conversions, which brings us to the next part. If we went back and looked at our conversion process, you see the answer and it's a nice simple line. We could look at this question, convert 2,437 inches into miles. And we just see it as a nice line. Right? You write down all the nice line. The problem with that nice line is that is the answer. You look at it and go, of course, I totally understand how to do this. Because you're literally looking at the answer. What should your notes look like? That. Your notes need to explain why you do every single conversion step. Okay? Your notes probably shouldn't get that gory because you could simplify and actually use numbers. Okay? But this was an exercise invented in this class to look at ways that we can establish conversions. Okay? And how we go about it. You should be thinking about the process used to solve. It isn't just multiply, divide, because that doesn't get you the correct process. Okay? With that, we'll go ahead and end a bit late.